Hello, my name is Liam Posher, and I'm here today to talk to you about electrostatic discharge (ESD) events, i.e. electric sparks, and how plasma chemistry inherent within these events, which takes the form of Joule heating, can drive hydrodynamic explosions. An explicit cartoon of our simulations is in the bottom left, while a movie showing results is in the bottom center. A common example of sparks occurs when walking across a carpeted floor in socks. A quick way to gauge your cat's temperament is to touch him on the nose after this. In this talk, I'll discuss the computational physics motivation for ESD simulation, what do we gain from it. Then I'll go into detail about empirical motivation for our assumed heat source. Then we'll dive into the validation and verification of the hydrodynamic simulations. After that, we will then probe the flow behind the shock front, and then wrap up with what we can excise from this work. ESD events are a nexus of electromagnetism, chemical kinetics, plasma physics, hydrodynamics, and statistical mechanics. They span length scales from nanometers to millimeters, streamers to spark channel length, and time scales from picoseconds to milliseconds, plasma chemistry to shockwaves. ESD events can result in a possible positive feedback loop where Joule heating within the center of the spark channel causes an increase in pressure, inducing advection, which in turn leads to an increase in the reduced electric field and other plasma variables, which then grows Joule heating. This decreased density would lower spark resistance, which raises energy delivered to a modeled circuit component, a victim load. We seek by simulation to declutter the complex network of energy pathways and enumerate energy terminuses. In this work, we show that a significant amount of energy goes into the hydrodynamic energy terminus. Hydrodynamic simulations are performed with a 3D Lagrangian code called Fiero. If we think of the 1997 movie Flubber, a green blob would either have a coordinate system moving with it in a Lagrangian frame or be moving through a coordinate lattice in a Eulerian frame. See the top right figure. A blind heat source approximating Joule heating is inserted into the hydro code causing advection. Cartoons showing our simulation are in the bottom left and center. Our simulations are the purple XY quadrant, which is one cell thick in the Z direction. A sample simulation image is in the bottom right, which shows three distinct regimes of fluid flow corresponding to channel, shock, and quiescent material. Our blind heat source proposed by John Rose is empirically motivated by legacy and current experiments done in Los Alamos National Laboratory, LANL, and Carl School of Mines, CSM. See the plots at the top right. These data share common features of fast rise times and a decaying peak exponential envelope. These features inform the temporal nature of our assumed heat source. We assume a Gaussian envelope for the spatial variation based on decades of substantiated literature. The four characteristic parameters of this heat source, Q of R, T, are Q naught, lambda R, tau R, and tau F, which are power density, radial channel extent, rise time, and fall time respectively. These parameters were varied, see figure at the bottom right, to validate our model against experiment. Q naught is a function of lambda R, tau F, and E naught over H, which is the energy per unit length deposited into the channel. How can we trust these simulations though? Legacy high-speed optical images recording direct spatio-temporal spark evolutions performed by Michael Murphy and Doug McHugh were used for experimental validation. These experiments were performed with Schlieren imaging of a spark channel created between two charged electrodes. A cartoon of the experiment is on the left, while high-speed optical images of the spark are on the right. These images have discernible shock front locations, but flow variables behind that shock front are not directly available. Experiments have perfect physics, but imperfect diagnostics. However, with experimentally validated simulations, we can probe the flow behind the shock front and determine theoretical regime applicability and the energy sunk into hydrodynamics. Simulations have perfect diagnostics but imperfect physics. To trust them, we require experimental validation. We calculated shock front location from experiments compared to the strong shock radius fit proposed by Lin. From this fit, we directly calculated energy going to hydrodynamics, see the center equation. We fit our proposed equation with variable A and B fit parameters to calculated shock front data. 4 experiments were analyzed that exemplified characteristic shock dynamics across a range of voltages. Several interesting structures and dynamics are readily observable from the optical data. Cylindrical to spherical geometry transition, channel boundaries, and the right-hand side plume near the sharp electrode. We calculated shock front locations in microns and nanoseconds and fitted our proposed equations. See the various colored plots below. All 4 experimental results with their fits can be seen in the top right plot. Variation of experimental A and B parameters are in the table. Comparing shock front data in our parameter space of simulations, we observe excellent agreement for the short fall times with tau F approximately equal to tau R, which corresponds to capacitive discharges. Fit parameters for experiment and simulations show good agreement with Lin's radial T to the 1/2 dependency. From the A fit parameter, we can determine our energy deposited per unit length E naught over H, which can allow us to calculate energy sunk into hydrodynamics. Now that we have a trusted, experimentally validated hydrodynamic simulation, we can probe the flow field structure behind the shock front. A sample simulation with the shown characteristic parameters for the blind heat source. Recall that Q0 is a function of all four parameters. By taking a radial slice along the yellow arrow, we obtain thermodynamic and flow variables behind the shock front for theoretical verification. The color in the figure corresponds to normalized density, with red being approximately 6, with the light blue being 1, and the dark blue asymptoting to 0. The horizontal axis is the x-coordinate, while the vertical axis is the y, with z coming out of the page. Mass density is the most informative variable due to conservation equation structure. Plotting density as a function of space and time, we observe several distinct regimes of flow. Within 20 nanoseconds on the spark timescale, not enough energy has been deposited into the channel to drive hydrodynamic advection. At around 30 nanoseconds, enough energy has been increased channel pressure for strong shock advection. As this shock expands outward, it loses strength after separating from the channel at around 75 nanoseconds. Lower slopes for the shockwave, white line, and channel boundary, gray line, indicate decreasing velocity. The top right plot is linear density, which is non-dimensionalized by ambient air density. At first glance, the dark blue region is uniform. This region is interpreted as being initially within the spark channel, approximated by the spatial extent of Joule heating. However, on closer examination of the log 10 of the density, in the bottom right plot, we observe a radial distribution within the current channel caused by continued advection. This continued advection ensures energy sinkage. We also compared to Lin's strong shock similarity solution, which assumed an energy line source in quiescent material. Lin's solution is shown on the left, with equations and variables correspondingly colored. Excising radial profiles of density from prior plots, we compare to Lin's density, see the figure on the right. At early times, we obtain excellent agreement. At later times, the simulation density decreases and diverges. Additionally, we consistently observe a kink in the simulated density. This corresponds to the channel discontinuity or material interface as seen in the Riemann breakdown problem or Schott shock tube. We've also observed similar behavior in several other codes we have used to study hydrodynamics and sparks. We use this experimentally validated and theoretically verified simulation to quantify energy deposited into the channel. All simulations are inherently wrong, but some can be useful if leveraged appropriately. We also test the applicability of the strong shock limit by looking at the overpressure, a normalized pressure, as a function of a normalized radial coordinate R0, where B is a fitted parameter that is calculated for different gases, P0 is ambient pressure, and gamma is the usual ratio of specific heats, a thermodynamic property of a material. All the simulations begin in the strong shock limit and eventually diverge to the intermediate shock limit as defined by Plooster. This transition is quantified by obtaining the location in space and time when the intermediate and strong shock overpressure diverges by more than 5%. Results of this calculation are in the left table and consistently occur on the order of 1,000 microns and hundreds of nanoseconds. Using the strong shock radial fits, we declutter the ESD energy web by quantifying the energy sunk into hydrodynamic advection as 1/3. In the left table, we report the specific experiment, fitted parameter for E0 divided by H, initial charge energy, and energy sunk into hydrodynamics based on the 6.28 millimeter air gap, and resultant energy percentage delivery. In conclusion, I have quantified the thermodynamic profile evolution behind the shock front in experimentally validated and theoretically verified simulations. Furthermore, I have showcased the domain of applicability for the strong shock limit for further analytical model leveraging. Lastly, I quantified the energy sunk into the hydrodynamic energy terminus in the ESD network budget in these spark regimes. Listed here are used references within this work. I'd like to thank Doug Tasker and Doug McHugh for current traces, providing firm foundations for our empirically motivated heat source. Additionally, I would like to thank Vincent Shearval and Jacob Moore for support in hydrodynamic simulations. Lastly, I'd like to thank the Weapons Systems Safety Analysis Group for the continued funding and support of this work.